And today I'm going to explain about the Poisson distribution and when the number of trials n is a binomial experiment increases to infinity, okay? The binomial distribution becomes the Poisson distribution. This is the example. Consider the transmission of n bits over a digital communication channel. Let the random variable x is equal to the number of bits in adder. The probability p that a bit is in adder is constant, and the transmissions are independent, following the binomial distribution. Let the mean large E large x is equal to lambda. Lambda is also equal to n multiplied by p. So based on this expression, the p can be equal to lambda over n, right? So this is the binomial distribution expression, right? The problem of x, when x is equal to small x, there will be binomial coefficient n by x multiplied by the probability to x's power multiplied by 1 minus p to n minus x's power, okay? That is the equation for the binomial distribution. And based on this equation, if we replace the probability to lambda over n, this can be rewritten as the binomial distribution n of n by x multiplied by lambda over n to x's power multiplied by 1 minus lambda over n to n minus x power, okay? We can simply change this equation to this. Now, suppose that the number of bits n increases infinitely, and the probability of an adder p decreases exactly enough that the multiplication of np remains constant. Then this will be changed to this. So based on this expression, we have to calculate the limit when n goes to infinite, the probability of x when x is equal to x, right? So we have to solve this one. And the first step, this can be changed to this one. Why? Because the limit when n goes to infinite, n by x multiplied by 1 over n to x's power can be rewritten as the limit when n goes to infinite, n factorial divided by x factorial multiplied by n minus x factorial, right? Multiplied by 1 over n to x's power, okay? And this can be rewritten, the limit when n goes to infinite, this can be n multiplied by n minus 1 multiplied by n minus 2 blah 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 multiplied by n minus x plus 1 multiplied by n minus x factorial, right? And this can be x factorial multiplied by n minus x factorial and multiplied by 1 over n to x factorial. Okay? So in this case, the n minus x factorial can be eliminated, right? Right? And this part should be equal to n to x factorial, n to x power. Why? N goes to infinite, right? So n is much, much higher than that of x minus 1. And also, n is much higher than 1, higher than 2, blah, 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 blah. So this can be simply expressed as n multiplied by n multiplied by n, blah, 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 right? So the number of n is x here. So this part can be changed to n to x's power. Okay? So this can be rewritten. The limit n goes to infinite, n to x's power divided by x factorial multiplied by 1 over n to x's power. Okay? Okay? So n to x power can be eliminated each other, right? So this can be 1 over x factorial. Okay? So this expression can be changed to 1 over x factorial when the number of bits n increases infinitely. And also, the 1 minus lambda over n to minus x power will be equal to 1. Why? Limit n goes to infinite, 1 minus lambda over n to minus x's power, right? So in this case, when we have n and n goes to infinite, this part will be equal to 0, right? So this can be, this part is eliminated, so there is no n here. So this can be simply expressed as 1 minus 0 to minus x power, right? No matter what x is, 1, 2, minus x power will be just 1, right? Right? So the second expression, 1 minus lambda over n to minus x power, can be equal to 1, okay? And this is the final expression. Limit when n goes to infinite, 1 minus lambda over n to nth power. And to calculate this, we have to first know about this relationship. The limit when x goes to infinite, 1 plus 1 over x to x power is equal to exponential. This is a very famous expression, okay, for the mathematics. And the one here is equal to the one here, okay? So if we change this expression to limit when n goes to infinite, 1 plus minus lambda over n to nth power this will be the exponential minus lambda. Okay? Because the 1 is replaced with the minus lambda here. So the 1 should be replaced with the minus lambda here as well. So we can have these three, the alternative expressions. So finally, we can rewritten this expression to n by x multiplied by 1 over n to x's power multiplied by lambda to x power multiplied by 1 minus lambda over n to nth power multiplied by 1 minus lambda over n to x power. These are the same equations, right? This equation is identical to this equation. Okay? And in this case, what is this? That is 1 minus x factorial, right? Here. And this is just x, the lambda to x's factorial, x's power, okay? And this equals to the exponential minus lambda. And this is just 1, okay? So finally, the limit when n goes to infinite, the probability of x when x is equal to x can be exponential minus lambda multiplied by lambda to x power over x factorial. Okay? So when the number of trials n goes to infinite, the binomial distribution can be simply changed to the Poisson distribution, and we can simply calculate based on this expression. In this case, the x can be from to infinite, but x should be integer value. 정수여야 하죠, x는. 여기서. So this is the definition of Poisson distribution. The random variable x that equals to the number of events in the given interval is a Poisson random variable. Why? Because given interval we cannot count the number of integer, right? So the Poisson random variable has the parameter lambda, which is equal to n multiplied by p, and that should be larger than 0. And then the probability mass function of x will be this equation, okay? This is the same equation. So the probability mass function of the Poisson random variable x can be exponential minus lambda multiplied by lambda to x power over x factorial. So we can use this equation to solve several problems. And this is the example 3-32, calculations for the wire flows. For the case of thin Cooper wire, suppose that the number of flows follows a Poisson distribution with a mean of 2.3 flows per unit millimeter. Let x denote the number of flows in 1 millimeter of wire. What is the probability that exactly 2 flows are obtained in 1 millimeter of wire? And according to the problem, we have to solve this problem based on the Poisson distribution. So the probability mass function of Poisson distribution will be E minus lambda to x's power over x factorial. So in this case, x denotes the number of flows in 1 millimeter of wire. So we have to find the probability that exactly 2 flows are obtained. So in this case, x should be equal to 2, right? And what is lambda? The mean is 2.3 flows per unit millimeter. So we have 2 unknown variables here. So we can calculate this, right? So we have to calculate the probability mass function of 2 that is equal to E minus 2.3 multiplied by 2.3 square over 2 factorial. And the answer will be 0.265. And what is the probability that 10 flows are obtained in 5 millimeter of wire? So in this case, the mean is given 2.3 flows per unit millimeter, right? But the problem was we have to find 10 flows in 5 millimeter of wire. So we have to change the lambda to 5 millimeter multiplied by 2.3 flows per millimeter. Okay? So the millimeter can be eliminated. So this can be 11.5 flows. That is the lambda for this question. And what is the x? X is 10. Okay? This is the lambda, and x is 10. So the probability mass function of 10 will be exponential minus 11.5 multiplied by 11.5 to 10th power over 10 factorial. This will be 0.113. And what is the probability that at least first flow is obtained in 2 millimeter wire? So in that case, let x denote the number of flows in 2 millimeter wire. So in this case, the lambda should be equal to 2 millimeter, 2.3 flows per millimeter, right? So the lambda can be 4.6 flows. And in this question, we have to find the probability that at least 1 flow is obtained. So we have to calculate the probability of x when x is larger than or equal to 1. Right? Right? So this can be written as 1 minus probability of x when x is smaller than 1. Okay? And as I mentioned in previous slide, x should be integer value. So this can be 1 minus probability of x when x is equal to 0. Okay? So this can be one minus E minus 4.6 multiplied by 4.6 to 0th power over 0th factorial, right? Because lambda is 4.6 flows here. So this should be equal to 1. This should be equal to 1. So finally, this should be 1 minus E minus 4.6. That will be 0.9899. Okay? So this is the probability that at least first flow is obtained in 2 mm wire. And this means that there is very high probability that we obtain at least first flow in 2 mm wire, right? And this is another example for the cities. The contamination is a problem in the manufacture of cities. Total particles of contamination that are on a city follows Poisson distribution. The average number of particles per square centimeter is 0.1. The area of a disk under this is 100 centimeters square. So let x denote the number of particles of our disk, and with that 12 particles occur in disk the study. In this question, the mean lambda is 0.1 particle. Per centimeter square, right? Average number of particles per square centimeter is 0.1. Okay? So lambda equals to 0.1 particles per centimeter square. Okay? But in this study, the area of a disk is 100 centimeter square. So the lambda should be changed to 100 centimeter square multiplied by 0.1 particles per centimeter square. 오케이? 그러니까 이게 저희가 지금 디스크에서의 컨테미네이션한 파리클 찾는 거잖아요. 그죠? 근데 문제에서 평균 값은 단위 센티미터 등 줬어요. 그러면 이 저희가 관심 있는 이 디스크의 평균 값은 0.1에다가 100을 곱해줘야겠죠. 그죠? 그 얘기입니다. So, the centimeter square can be eliminated and this can be 10 particles. Okay? And in this question, we have to find the probability that 12 particles in the disk, right? So, x is equal to 12, right? So now we can solve this problem. The probability mass function of 12 is equal to E minus 10 multiplied by 10 to 12th power over 12 factorial. And this is equal to 0.095. Okay? And this is another question. What is the probability that zero particles occur on the disk. We can use the same lambda here, right? Because we can use the same disk here, but the difference is that x should be equal to 0 rather than 12. So this will be e minus 10 multiplied by 10 to 0's power over 0 factorial. This goes to 1, this goes to 1. So this is equal to e minus 10, and that is equal to 4.54 multiplied by 10 to minus 5th power. Okay? And this is the last question. And what is the probability that 12 or fewer particles occur on the disk? And in this question, we have to find the probability of x when x is smaller than or equal to 12, right? And this can be the summation of probability of x when x is equal to 0, and the probability of x when x is equal to 1, blah, 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 plus the probability of x when x is equal to 12. Okay? And this can be re-expressed by the summation of I from 0 to 12 exponential minus lambda. Lambda is 10 here, right? So minus 10 multiplied by 10 to i's power divided by I factorial. Okay? So you can calculate this equation, this summation from 0 to 12. Okay? So this is the answer for this question. And this is about the Poisson mean and variance. If x is a Poisson random variable with parameter lambda, lambda is equal to n multiplied by p, then the mean is equal to lambda. Okay? And also the variance is equal to lambda. That is the definition for this Poisson distribution. So if the mean and variance of the Poisson distribution are the same, and if the mean and variance of a data set are not same, the Poisson distribution shouldn't be applied. Okay? So before starting to solve some problem, you can check whether the mean and variance are identical to decide whether you can use the Poisson distribution or not. Okay? So if you think that, if you obtain that the mu and variance is identical, you can think that probably you can solve some problem based on this Poisson distribution. Okay? So this is the end of chapter 3 regarding the discrete random variable. And we're going to study the continuous random variable today. The only difference between the chapter 3 and chapter 4 is discrete or the continuous. Okay? So this is the analysis of continuous random variable. That is chapter 4. And this is the chapter outline. The first, we're going to learn about what is the continuous random variables. And secondly, we can learn about the probability distributions and the probability density functions. So we use the probability mass function for the discrete random variable, right? But in this case, we have to use the probability density function. The only difference between the probability density function and mass function is we can use this for the continuous random variable, and we can use the probability mass function for the discrete random variable. But you can see the difference between the probability mass function and density function in the later slide. Okay? 그러니까 continuous random variable일 때는 probability density function이라는 용어를 쓰고요. 그리고 discrete random variable 챕터 3 같은 경우는 probability mass function을 썼습니다. 그죠? 근데 둘 다 컨셉은 똑같아요. 근데 뒤에서 설명 다시 드리겠지만 discrete는 셀 수가 있으니까 시그마, 서메이션으로 했죠. 이거는 뭐가 되겠죠? 당연히 인테그랄이 되겠죠. 적분이 되겠죠. 고차예요, 고차. So thirdly, I'm going to explain about the cumulative distribution function and mean and variance of a continuous random variable. And I'm going to explain about the continuous uniform distribution and the normal distribution, which is called 정규 분포 in Korean. And normal approximation to the binomial and Poisson distributions, and the exponential distribution, and Allang and gamma distributions, and wave distribution, and finally, I'm going to explain about the log normal distribution. So, these are the chapter outline for this chapter 4. This is the learning objectives for the chapter 4. After careful study of this chapter, you should be able to do the following. First, you can determine the probabilities from the probability density function. And you can determine the probabilities from cumulative distribution functions, and the cumulative distribution functions can be obtained the probability density function and the reverse. And you can calculate the means and variances for the continuous random variables. And you can understand the assumptions for some common continuous probability distributions. And you can select an appropriate continuous probability distribution to calculate the probabilities for specific engineering applications. And you can calculate the probabilities, and you can determine the means and variances for some common continuous probability distributions. And you can standardize the normal random variables. And you can use the table for the cumulative distribution function of a standard normal distribution to calculate the probabilities. And finally, you can approximate probabilities from sum and Poisson distributions. So, after finishing the chapter 4, you can do categories. So, what is the continuous random variables? This is the example. The dimensional length of a production is subject to small variations in measurement due to several reasons, such as vibrations and temperature fluctuations and operator differences and cutting tools and raw material changes. So this length x would be a continuous random variable that occur in an interval of real number. So the possible values of x is uncountable. So I'm going to explain this based on this schematic description. This is the bar, okay? The original length of bar is x, okay? So if there is no effects, there is no reasons that affect to the length change through this, It will be the exact value, okay? But as you can see here, there are several reasons to change the length of this bar, such as vibrations and temperature variations and operator differences and the cutting tooth and low material changes and etc. So this length can be changed, right? For example, the length can be increased to A, right? Because of these several reasons. And also, the length can be decreased as well, right? By these several reasons. So, this can be B. So, what is the X in this case? The X should be larger than or equal to A and smaller than or equal to B. Okay? Because the length of the bar is affected by so many reasons, so there is only one way we can express the length is the interval from A to B. But in this case, can you calculate the number between this interval? We cannot calculate, we cannot count, okay? So this is uncountable case. So this is called the continuous random variable. Okay? So in the case of the discrete random variable, we can count the number of items in the set, right? But in this case, we cannot count the number of items. So it is normally expressed by this interval. So that is the definition of the continuous random variable, okay? And this is the definition of the density function, which is called 밀도함수 in Korean. The density function, which is in contrast to the mass function, distribute the probability continuously along an interval. As I explained in the previous slide, mass function is only applied to the case of discrete random variable, but the density function is only applied to the continuous random variable. That is the difference. And this is the typical example of the density function. And if we assume that this is the long and slender bar, and the length is x, and this is the loading, okay? There is a distributed loading here, and the total loading on the beam between the point A and B calculated by the integration of this area, right? Okay? So the loading in this case will be the density function. So the total loading can be calculated by the integration of the density function. This is the density function from A to B. So we can calculate the total loading based on the concept of density function here. When x is expressed as the interval between A and B. And what is the probability density function? The probability density function, fx, describes the probability distribution of a continuous random variable x. And this is the typical description to explain about what is probability density function. And x-axis indicate the continuous random variable, okay? And y-axis indicate the probability density function, okay? So this curve can be expressed by the probability density function, right? According to the x. So in this case, what is the probability of x when x is between A to B will be this shaded area. And this shaded area can be calculated by the integration, right? Integration of the probability mass function from A to B. Okay? That is the probability of X between A and B. Okay? So, for the continuous random variable, we can use this integration formula to calculate the probability instead of the summation. This is the definition of the probability density functions for a continuous random variable x, which is a probability density function fx, is a function such that the probability density function should be larger than or equal to 0. There will be no minus probability density function. And the integration of probability density function from minus infinite to infinite will be 1. Okay? And the probability of x when x is larger than or equal to a and smaller than or equal to b should be equal to the integration of probability density function from a to b. Okay? And this is the area under the probability density function from a to b when any a and b are applied. So these are the very important definitions, the characteristics of the probability density function. And now I'm going to explain about the histogram. A histogram is an approximation to a probability density function. Each rectangle has a base representing an interval of the data value, and base multiplied by height of the rectangle create an area. And this is the typical example for the histogram. And x-axis indicate the continuous random variable, and y-axis indicate the probability density function here. And these are the probability density function, okay? But if we cannot solve the probability density function based on the equations, mathematical equations, we can simply calculate this area by using these small columns, right? And this is the base, which is the interval between the previous x and the next x. And this is the average height at this point, okay? And if we calculate this area, if you calculate this block, rectangle here, this area should be close to this area, right? 요 베이스의 중간값에 대한 상응하는 값을 높이로 잡고요. 그리고 요 두 개의 베이스를 가질 때 이 사각형의 면적은 요 구간에서 요 커브 안의 면적하고 유사해요. 그죠? 만약에 베이스를 줄여주면 줄여줄수록 이 편차는 줄어들겠죠. 그죠? 그래서 만약에 그 probability density 펑션이 인테그레이션이 안 되게 나올 수가 있잖아요. 그죠? 경우에는 이거를 적분해서 할 수가 없기 때문에 그냥 히스토그램을 그려서 어프록시메이션으로 계산하면 돼요. 아시겠죠? So normally actually in the engineering field, this is very popular solving method to calculate the area under some nonlinear curve. So this is the definition of the histogram. And this is very powerful tool actually for the engineering field. And this slide is about the area of a point. Each point has 0 probability since a base is 0. Therefore, if x is a continuous random variable, for any x1 and x2 should satisfy these four expressions. Based on this graph, if if there is one point here, what is the probability for this case? There should be 0, right? Because the base is equal to 0. So the probability of x when x is larger than or equal to x1 and smaller than or equal to x2 should be equal to the probability of x when x is larger than x1 and smaller than or equal to x2. And also, this should be equal to the probability of x when x1 is larger than or equal to x and the x is smaller than x2. And finally, this should be equal to the probability of x when x is larger than x1 and smaller than x2. Right? Because the probability of x when x is equal to 1 and the probability of x when x is equal to x2 should be equal to 0. Okay? So this means that the probability of x when x is equal to a certain x here, that should be equal to 0. So that is the definition for the case of the continuous random variable. And this is the example 4-1. For the electric current, let the continuous random variable x denote the current measured in a thin copper wire in milliamperes. And assume that the range of x is between 0 and 20 ampere. And the probability density function fx is equal to 0.05. And in this case, what is the probability that a current is less than 10 milliamperes? And we can draw this curve. This is the probability density function, and this is the x, right? Continuous random variable. And in this case, the range of x is between 0 to 20 milliampere. So the range will be 0 to 20 milliampere. So in this case, the probability density function is 0.05. There is the constant value. That is 0.05, right? So the problem is that what is the probability that a current is less than 10 milliampere? This is the 10 milliampere. So in this case, we have to calculate this shaded area, right? So the probability of x when x is then n can be the integration of probability mass function from to 10, right? And this will be the integration of 0.05 dx from 0 to 10. And this is equal to 0.05 x from 0 to 10. Okay? So this will be 0.05 multiplied by 10 minus 0. So that is equal to 0.5. Okay? So if the probability density function is expressed as the constant value, it is very easy to solve the problem. Okay? And if the range of X is between 5 and 20 milliampere, what is the probability? So for this question, we have to find out the area of this shaded area, right? So there will be the probability of X when X is larger than 5 and smaller than 15. Oh, 20. So this is the 20, okay? So this should be 20, okay? And that is equal to the integration of 0.05 dx from 5 to 20. And that is equal to 0.05 multiplied by x from 5 to 20, okay? And that is equal to 0.05 multiplied by 20 minus 0.05 multiplied by 5. That is equal to 1 minus 0.25. So the answer will be 0.75. Okay? Okay. So it is very easy to solve when the probability density function is expressed as the constant value. And this is another example for the hole diameter. Let the continuous random variable x denote the diameter of a hole drilled in the sheet metal component. The target diameter is 12.5 millimeters, and the random disturbances to the process result in larger diameters. So the historical data shows that the distribution of x can be modeled by this probability density function, okay? Fx is equal to 20 multiplied by exponential minus 20 multiplied by x minus 12.5. But in this case, the x should be larger than or equal to 12.5 millimeters, right? Why? The target diameter is 12.5 millimeters, and the random disturbances only result in larger diameters. Okay? 그러니까 구멍을 더 크게 만드는 효과만 준다는 얘기. 그러니까 작아질 수는 없어요. So if a part with their diameter larger than 12.6 millimeter is scrapped, 버려지는 거예요, 그냥 버리는 거예요. What? Scrapped. So And this is the probability density function. And the 20 multiplied by E minus 20 multiplied by x minus 12.5 follows this curve. Okay? And based on this question, the x should be larger than or equal to 12.5. The starting point is 12.5 here. And in this case, first we have to find out the proportional part in which have the diameter larger than 12.6, right? So we have to calculate this shaded area. And this shaded area will be the probability of x when x is larger than 12.6 equals to the integration of the probability density function from 12.6 to infinite, right? So this will be the integration 20 e minus 20 x minus 12.5 dx from 12.6 to infinite. Right? And this will be minus e minus 20 x minus 12.5 from 12.6 to infinite. Right? 이거 미분하면은 요거죠. And this will be minus e minus 20 infinite minus 12.5 minus e minus 20 12.6 minus 12.5. Okay? Okay? And what is the e minus infinite? 0. So this goes to 0. So the answer will be plus e, right? Minus minus is plus. Plus e minus 20 multiplied by 0.1. Okay? That is 0.13. Okay. And what proportion of part is between 12.5 millimeters and 12.6 millimeters? That is this yellow shaded area, right? So the probability of x when x is larger than 12.5 and smaller than 12.6 will be the integration of 20 e minus 20 x minus 12.5 dx from 12.5 to 12.6. Okay? And this will be minus E (20x minus 12.5) from 12.5 to 12.6. Okay? And this will be minus E minus 2, right? Because if we substitute x to 12.6, this part will be 0.1. So 0.1 multiplied by 20 is 2. And plus, right? Because minus is minus here. Double minus is here. So what is the e to 0th power? Oh, there is 1. So this is 1. Okay? So what was this? In the previous case, there was minus 0.135, right? Plus 1. That is equal to 0.865. Okay? So we can simply solve the probability for the case of the continuous random variable by using this integration formula. And now I'm going to explain about the cumulative distribution function. The cumulative distribution function of a continuous random variable x is expressed by this equation. Large F large X is equal to the probability of x when x is smaller than smaller x. That is equal to the integration of the probability density function from minus infinite to infinite. Okay? In this case, we have to find out the shaded area up to the x point, right? This is the x point. So we just simply substitute the x here to another symbol, okay, to avoid the duplication. So we just choose u. So you can choose a and b and other characters as well, okay? Just we choose u to avoid the duplication of using the x. Okay? 그러니까 지금 x까지의 면적이잖아요. 컴퓨터면 누적이니까, 그죠? 지금 시작점은 없고 마이너스 인피니티부터 어떤 probability density function 커브가 있을 때 x 포인트까지의 면적을 구하는 거잖아요. 그죠? 그죠? 근데 x를 지금 여기서 썼어요, 한번. 그죠? 그러면 보통 저희가 여기다 x, fx, dx라고 썼는데 x가 좀 겹치잖아요. 그죠? 그럴 땐 그냥 다른 캐릭터를 써야 되죠. 아무거나. 그래서 그냥 u를 사용한 거예요. 이게 a가 돼도 되고 b가 돼도 되고 c가 돼도 상관없어요. 아시겠죠? So in this case, the x should be between minus infinite to infinite. Okay? And this is the example. For the Cooper wire current measurement in the previous example 4-1, the cumulative distribution function consists of 3 expressions to cover the entire real number line. First one, when x is smaller than 0, the fx probability density function should be equal to 0. In the example 4-1, the probability mass function was expressed by this figure, right? So there is only probability density function between 0 to 20. That means if x is smaller than 0, the probability mass function should be equal to 0. Okay? So the cumulative distribution function should be also equal to 0 when x is smaller than 0. Okay? And the cumulative distribution function from 0 to x when x is between 0 to 20, that is equal to 0.05, right? Why? Because the integration of probability density function from 0 to x when x is between 0 to 20, that can be 0.05 dx, right? Because in this case, the probability density function is just 0.05 here. And this also can be 0.05 x, du. Okay? This is u, okay? From 0 to x, right? And this will be 0.05 x minus 0. Okay? So the cumulative distribution function when the x is between 0 to 20 will be 0.05x. And when x is larger than 20, the cumulative distribution function should be equal to 1, right? Because this shaded area is equal to 1. So we can express the cumulative distribution function large f large x is equal to 0.05 x and 1 when x is smaller than 0 and x is between 0 to 20 and x is larger than 20. Okay? Okay? So this is the cumulative distribution function for this case. And we can also draw this figure. This is the continuous random variable x. And this is the cumulative distribution function large f large x. And if we indicate that this is the 0 and this is the 20, when x is smaller than 0, the cumulative distribution function will be 0, right? And when the x is between 0 to 20, the cumulative distribution function increases linearly, right? Because this is the linear equation, 0.05 multiplied by x. And this point is 1, right? And when x is larger than 1, the cumulative distribution function should be equal to 1. Okay? So this is the description for the cumulative distribution function. Okay? So this is end of today's class, and see you on Friday.